Today I'm gonna briefly introduce quite another materials called polymer derived ceramics, and this presentation will introduce how to coating this polymer derived silicon carbide ceramics on the commercial carbon fiber. Okay, and first I'm gonna briefly introduce what the motivation of this research is. Basically, my research objective is try to replace defense constraint products called Kevlar fiber for defense or some military applications. And is it possible to create a composite to replace the Kevlar fiber by using the commercial carbon fiber? Okay. And we can also reduce the weight and increase the strength. Okay, so how to work on this? Basically, we just simply by the spray coating of this beside the liquid-based polysilicide pre-ceramic precursor on this commercial carbon fiber. Okay, so that's just our basic process. We just spray coated this polysilicide pre-ceramic precursor on the commercial carbon fiber. Okay. Of course, this coating can provide the corrosion resistance and strengthen the strength of this commercial fiber. Okay. So what is the polymer derived ceramics? Okay, or we can call it PDC. It's commonly use the pre-ceramic precursor backbone based on the silicon and adjusted the molecular weight with two important parameters: the group X. Okay, or we say it's a functional groups on a polymer backbone, and the substitute R1 and R2 connected to the silicon, right? Therefore, we will define a ceramic type based on this functional group. Okay, for example, if it is a silicon carbon bond, we can say it's the poly carbon silent. We can, after pyrolysis, the poly carbon silent will form. Okay, and if it's the silicon oxygen bond, we say it's a polysiloxane. Okay, and so on and so on. Due to its liquefies properties, it's simple to fabricate or foaming. Okay, either it can be foamed by casting, inject molding, pressing 3D printing, and like I saw the spray coating and so on. Okay. So, as what I mentioned previously, the ceramic type after pyrolysis, depending on the silicon bonding with the functional group, right? Carbon, oxygen, some metal or nitrogen. And what I'm gonna introduce you guys here is the silicon carbon nitride, okay, ceramics. Okay, so this precursor will transfer from the ceramic phase to the polymer, from the polymer phase to the ceramic phase, depending on the pyrolytic temperatures. Okay, so roughly the temperature reaches like 1,000, 1,200. This precursor, pre-ceramic precursor, start to crystallize, depending on the temperature and pressure and so on. Okay, and there are some application already like the silicon carbon oxycarbon based ceramic glow plug or some brake disc and the sensor and so on, because it's a semiconductor. Okay, so what is our experimental methods? As what I mentioned previously, we use the Formosa plastic, the pen based long fiber used as the reinforced materials. Okay, and we spray coated this polysilicide pre-ceramic precursor and incorporated with graphene to strengthen the strength of this commercial carbon fiber. Okay, so this is our steps. We just spray coated and we just preheat it at 150 and for the partial cross linking, and then we work on this final pyrolysis in the inner gas. So this is the two types of the composite, this polymer ceramic composite. So basically, we have this commercial carbon fiber, and we spray coating this pre-ceramic precursor, and also we incorporated with the graphene in this liquid-based pre-ceramic precursor, and then we spray on this commercial fiber. Okay, and finally we just pyrolyze it in the inner gas. Okay. So these are our experimental parameters. Basically, we define this precursor in the PSD, okay, and with different concentration diluted by acetone, and we incorporate this pre-ceramic precursor with graphene with different weight percent in this pre-ceramic precursor. Okay. Okay, so this is our pyrolytic temperature. We pyrolyze in 200 something, 300 and 400 and so on. Okay, the highest pyrolytic temperature is 750 Celsius. Okay, so this is our sample. We do the tensile test. We just use two of carbon fiber, some glass fiber plates to clamp this this fiber, our samples. Okay. And we do this called the three electron method, or we can say it's a potential dynamic polarization to measure its corrosion resistance. Okay, I show you some results. This the first SEM image shows this commercial carbon fiber, and we coated this pre-ceramic precursor and pyrolyzed at the 350, 450, and 750. Okay, and obviously we saw a lot of cracks form when the pyrolytic temperature reached 750 Celsius. Okay, so that's mean higher temperature maybe not quite suitable for strengthening this commercial carbon fiber. Okay, so I quickly show you some data. This is specific strength. That means we use the tensile strength divided by the density of this composite. Okay, so when we have the 40% of the pre-ceramic precursor pyrolyzed at 550 Celsius, okay, the specific strength increased almost 40% compared to the pure carbon fiber. Okay, and the specific strength incorporate with graphene content. We can see when this pre-ceramic precursor contain 0.5 weight% of the graphene, okay, its specific strength increase also almost higher than the 70%. Okay, and this is the specific modulus. The same, we use the concentration of the 40% of this precursor pyrolyzed at 550. Okay, and the modulus it has by about 15%. Okay, and also we incorporate the graphene about 0.5 weight% in the pre-ceramic precursor. And this modulus, specific modulus, increased almost 60%. Okay, so the graphene enhance this mechanical strength due to its orientation. Okay, I just want to show you no matter how its orientation of this graphene, except for this case. Okay, other orientation of the graphene, either it's few layer graphene or graphite, no matter what, mostly it can enhance the mechanical strength of this commercial carbon fiber. Okay, so this is a summary table. I show you mostly this Young's modulus, tensile stress, specific strength, and the specific modulus almost increased. Okay, also as I mentioned, I do the 3-point test or the potential dynamic test showing that obviously the this is a TAFO curve, shows the potential corrosion potential increase, and the corrosion and the current density decrease. Okay, that's mean after coating this fiber or carbon, it's not easy to oxidize. Okay, and this the graphene incorporated have the same trend of this corrosion resistance. Okay, so I compare with other metals with its corrosion rate, and our study is pretty low compared to others. Okay, even it's pretty low compared to the high entropy alloy. Okay, so that's our conclusion. I will show you some results. We have this without graphene content composites and its strength and modulus increase, and with graphene content composites and its strength and specific modulus also increase a lot. Okay. Okay, and for this corrosion test, we have the higher potential, higher corrosion potential and the lower corrosion current. Okay, that means we improve a tremendous improve its corrosion resistance. Okay, so it's my presentation. Thank you very much.